Hello everyone. Today we will discuss about PDV work or displacement work of the piston in a cylinder for non-flow or closed system. So you can see here in this figure, this is a cylinder. This is piston, okay, and this piston is at IDC inner dead center position. So this is actually state first of this piston, state first of this system. So actually this piston in this cylinder is at point 1. Suppose this is point 1, this state. So this is actually moving IDC to ODC like this due to the combustion or expansion of burnt gases in this cylinder. So here in case of state first, pressure inside this cylinder is P1, volume V1, temperature is T1, and this piston is moving left to right, means IDC to ODC. IDC is inner dead center, ODC is outer dead center. So this piston cannot move this IDC to left direction, because it is the last position of this piston to move in the left direction. So this is the dead position of the piston to move in the left direction. Similarly, it is the dead position of the piston to move in the right direction. So this piston cannot move in the right direction after this ODC, and this cannot move in the left direction after IDC. So this is inner dead center and this is outer dead center. So here in the first state, pressure is P1, volume V1, temperature is T1, and in the second state of the piston, so piston is moved from this position to this position. Okay, so due to movement of this piston, so this piston is displaced from state 1 to state 2. So this is state 2. Okay, so here you can see pressure is increasing, or pressure is P2, volume V2, temperature is T2. Because this piston is moving IDC to ODC, it means expansion is taking place during this process. So during the process of expansion, volume will be increased. If volume is increasing, then pressure will be decreased. Okay, so here you can see when this piston is moving IDC to ODC. So this is state first and this is state second of this piston, and this vertical line is indicating pressure variation and this horizontal line is indicating volume variation, and this is 0 point origin point. At this point pressure and volume both are 0. So pressure is increasing in upward direction and volume is increasing in left to right direction, in this direction. So here you can see the expansion of process 1 to 2 is taking place. So simply we can say here this is state first, this is state second. So between state first and second, this is the distance delta x. Suppose this is delta x, so this is projected here. So this is actually you can say this is x or L or delta x. So this is a small displacement of this piston, and which is equal to dx, and during this displacement of the piston, volume covered by the piston is dV. So this is a variation of volume during process 1 to 2. Also the displacement of this piston during 1 to 2 is dx. Okay, so when the piston moving IDC to ODC, expansion is taking place from state first to state second, then this distance or displacement of piston will be, suppose it is dx. Okay, and here dx is displacement of the piston. Okay, and A is area of cross section of the piston. Then we can say force exerted on this piston by the gases F is equal to P dot A. Okay, then we can say work done by the piston W is equal to force into displacement F dx. Okay, so now we can place the value of F in this equation. So this will be equal to P A into dx, and this term will be equal to dV. So simply we can say the displacement during process 1 to 2 W1 to 2 is equal to integration of P dV. So this is applicable only for reversible process, not for irreversible process. Okay, so now there may be different conditions of this PDV work. Either pressure may be constant, volume may be constant, temperature may be constant, entropy may be constant. So we will discuss about different conditions to apply this PDV work or formula. So actually there are the following conditions. So first condition, system should be enclosed should be a closed system. Okay, second condition, process must be reversible, and third, it may be expansion will be positive and compression will be negative. So first case, if volume is constant, then dV is equal to 0, because V1 is equal to V2 is equal to V3. It means dV is equal to 0. Then W1 to 2 is equal to integration of P dV will be 0, because dV is equal to 0. So here work done during this process at constant volume will be 0. Here you can see this is process 1 to 2. volume is not changing throughout this process because this distance is constant. So this distance is showing the volume. Okay, so this is zero line, so volume is changing here to here. So at each and every point of this process volume is not changing, that's why volume is constant, then dv is equal to 0. If dv is equal to 0, then w1 to 2 will be 0. So during the constant volume process or isochoric process, this is also called isochoric process, work done is 0. So in second case, you can see this is a constant pressure process or isobaric process, process 1 to 2. So you can see during this process pressure is constant, P1 is equal to P2, but volume is V1 here and volume is V2 here. So delta will be there, delta V. So delta V is not equal to 0 because this process is having area 1 to A B. So area is not 0 here because volume is changing. So here we can say work done 1 to 2 is equal to P dV. Okay, now we will discuss about the third process or third condition. If temperature is constant, means it is isothermal process. So we can say T is equal to constant from ideal gases. PV is equal to PV upon T is equal to P1 V1 upon T1 is equal to P2 V2 upon T2 is equal to constant. Okay, if T is constant, then we can say PV is equal to constant because T to T is cancelled, T is common. So we can say PV is equal to constant, or we can say P is equal to C upon V. P is equal to C upon V, or P is equal to P1 V1 upon V. Okay, so simply we can say work done W1 to 2 is equal to P dV is equal to, place the value of P this, so this will be 1 to 2 C upon V dV. So this will be actually uh, W1 to 2 C ln V2 upon V1, or we can say C is equal to P1 V1, C is equal to P1 V1. So this will be P1 V1 ln V2 upon V1. Okay, or we can say W1 to 2 is equal to MRT1 ln V2 upon V1, V2 upon V1, because PV is equal to MRT, PV is equal to MRT. That's why we can write this formula like this. Okay, so for the isothermal process, we can say work done by the piston W1 to 2 will be equal to MR T1 ln V2 upon V1. Now we will discuss about adiabatic process. So in case fourth, for the adiabatic process, we can say This will follow the law PV gamma is equal to constant in case of adiabatic process. So a process is said to be an adiabatic process if there is no heat transfer to the system or from the system to the system or from the system. So for an ideal gas, we can say PV gamma is equal to constant is equal to P1 V1 gamma is equal to P2 V2 gamma, or simply we can say P is equal to C upon V to the power gamma is equal to C V to the power minus gamma. And now we can say work done during this adiabatic process 1 to 2 is equal to P d V. Okay, now we will place the value of P here. So this will be actually C V to the power minus gamma into dV. Okay, now we can say W1 to 2 is equal to C is common V to the power minus gamma plus 1 minus V1 to the power minus gamma plus 1 upon minus gamma plus 1 limit 1 to 2. And this will be actually C V to the power minus gamma plus 1 minus C V1 to the power minus gamma plus 1 upon minus gamma plus 1. So here we can say C is equal to P1 V1 to the power gamma C is equal to P1 V1 to the power gamma, also C is equal to P2 V to the power gamma. So we will place this value here for C. So this will be actually P2 V to the power gamma into this value V to the power minus gamma plus 1 minus C is equal to P1 V1 to the power gamma P1 V1 to the power gamma into this value V1 to the power minus gamma plus 1 upon minus gamma plus 1. So now we can say this will be equal to P2 V to the power minus gamma plus 1 plus gamma, okay, minus P1 V to the power V1 to the power minus gamma plus 1 minus gamma plus 1, and another power is gamma. So this will be cancelled, this will be cancelled, and here this is 1 minus gamma is equal to, this can be written as P2 V2 minus P1 V1 upon 1 minus gamma. Also we can say this term can be written as minus P1 V1 minus P2 V2 upon minus gamma minus 1. So minus to minus cancel. This is equal to P1 V1 minus P2 V2 upon gamma minus 1. So simply we can say work done 1 to 2 during adiabatic process is equal to P1 V1 minus P2 V2 upon gamma minus 1. So this is the work done during the adiabatic process by the piston. Okay, so last condition is for the polytropic process. So case fifth, work done by the piston during polytropic process 1 to 2. Okay, so in case of polytropic process, simply we can say this is the graph, means PV diagram for this polytropic process 1 to 2, 1 to 2. So this is actually shaded area. Okay, so actually in this case, this will follow the law PV to the power n is equal to constant, and in previous case it was following the law PV to the power gamma is equal to constant. So only difference of is gamma and n. So n is the polytropic index. So the same relation will be there for this case. So we can say polytropic process is called polytropic when the pressure and volume both follow the law P V to the power n is equal to constant. Okay. So simply we can say P is equal to C upon V to the power n. Okay. Or we can say this will be equal to cv to the power minus n. Then we can say w1 to 2 is equal to p1 v1 minus p2 v2 upon n minus 1. So this is work done by the piston for a polytropic process, because this is following the law p v to the power n is equal to constant. So this formula and this formula both are similar, only is difference of gamma minus 1 and n minus 1, and gamma is equal to 1.4. So we can also say n is greater than 1 and less than gamma. Thanks for watching this video. All the best.